So today as Alithia has very rightly pointed out about the performance improvements you will get with OFDMA. So here on the plate comes a different perspective from simulation results. So we don't have access to so many devices, real devices. So here we come about simulations perspective on Wi-Fi 6 OFDMA. I am not going into details as to how OFDMA works and all. So this is my outline of today's talk. So first I am going to discuss results about no OFDMA versus OFDMA. So when I say no OFDMA, it's 11x but single user, not OFDMA. And then like OFDMA under different applications. So the question we ask is that when is multiple access beneficial? So, to investigate that, so what we do is that we compare OFDMA versus non-OFDMA under varying traffic loads. We take 5 Mbps to 245 Mbps. We are taking 245 Mbps because MCS 11 corresponds to a bit rate about 240 Mbps. So, which is why low load to high load. So for this we use a network simulator platform which is NS3, and specific version that we have used is NS 3.34. So this NS3 version supports a very simple scheduler which is round robin scheduler. So what it does, every time it breaks into equal parts and then assigns to the clients. So it also allows you to configure that at how many splits you want to split your bandwidth to. You can set it to 1826 tones or 852 tones and so on. So these configurations you have on the plate to vary upon. So only thing the scheduler will do, that whatever split you have taken, it will allocate the users in a round robin fashion to these splits. Okay, and so as I said that you have the non-OFDMA version as well, which is the single user version. So the transmission happens in this way, that the downlink transmission that goes into, it has a multi-user block acknowledgement request along with the PSDU that is getting transmitted, and then block acknowledgement goes from the clients to the AP. For this is for downlink transmission. And this is our setup, which is we have about 40 clients and those 40 clients are within 5 meter proximity of the AP. So, it is a very good channel conditions. Everybody is operating upon MCS 11, which is a base that you can imagine. So, we started with based conditions, even to see even in based scenarios can OFDMA give benefits. So, then our bandwidth was 40 megahertz, MCS was 11 as I said. We used both transport protocols UDP and TCP. So, payload was this, and this is the simulation parameters that we have used. So, please focus on the transport protocol, the scheduler, and simulation we have run it for kind of 10 seconds to get a stabilized results. So, aggregation is enabled, MPUDU aggregation is enabled as it is, MSDU was disabled. So, we did not touch upon the aggregation. So, we let that happen as it wanted to do upon. So, the physical rate that you will get at MCS 11 is around 243 Mbps. That is why our the last traffic load that we supported was 245 Mbps. And these are different RU configurations we tried upon 1826 tones, 852 tones and so on. This you can see. So, we worked on a 40 megahertz bandwidth. And so, the traffic rates that we analyzed, high downlink traffic load, which is 245 Mbps, intermediate 120 Mbps, low downlink 5 Mbps. So, I will explain the UDP results first because that is easier to understand. Then I will go over to TCP results. So, in UDP case, so as I said that there is downlink OFDMA support, and since in UDP there is no uplink scenario, so it is only downlink, there is absolutely no collision either in OFDMA or non-OFDMA. There are no collisions, only downlink transmissions are happening. So, here if you look that, so this graph shows aggregate throughput with traffic load, and this graph shows average latency. So, I will come to each of it. So, first of all let us look at high traffic load, which is 245 Mbps. So we see that no OFDMA shows highest throughput, which is the orange bar. Like the other, so we, as I said, that we tried with various configurations, RU configurations, and out of this, like non-OFDMA provided the highest throughput, which corroborates with Alethea's results. Next, we found out that no OFDMA shows even lowest latency, which is unlike what they had reported. Here we see that no OFDMA was the one who reported the lowest latency. This is for high traffic load. Then when we tried to understand that why did it was the case that like non-OFDMA was the winner, so then we looked at aggregation statistics, and the x-axis shows various configuration, y-axis shows the aggregation label that has been there. For no OFDMA, you see that maximum like aggregation is 64 and there are some 17. For non-OFDMA, as you keep on increasing the number of RUs, the aggregation is limited. Okay? So, the aggregation can get limited by two reasons in high traffic load. Firstly, either because if you aggregate more, you will exceed Tx op, or if you aggregate more, then you will exhaust the sequence space. Remember that aggregation has a sequence space of 64 in this simulation result that you have taken 64. So, either it will exceed the sequence space or it will exceed the Tx op limit. So, in this case it was 64 by no OFDMA because beyond 64 it was not possible. For these guys it was less than that because it was exceeding Tx op. Okay, and this means that non-OFDMA was not exceeding Tx op, it was getting limited because of it is going over the sequence space. Then yes, so then if you look at this table, let us look at this table in a great detail. So, if you see that total number of transmissions that happen, so the way we look at the matrix is that we take a Tx op time limit which is about 5 millisecond and then we report the matrix. So, then like this is averaged across all those 10 second, we had like around 1000 plus Tx op duration. So, then that's what we look at. So, if you see that in a Tx op, non-OFDMA made around 3 transmissions, whereas OFDMA configuration made only 1 transmission. This also proves the point that in non-OFDMA the transmission was, the aggregation was limited because of sequence space, not because of Tx op. Here, because that is why you see that more 3 transmissions are happening, and here the number of stations served of course is higher. For 4 cross this is 418 and this one. Now, if you see the number of frames transmitted, okay. So, if you see the number of frames transmitted, you see that total number of frames transmitted with non-OFDMA is higher, okay, than the other counterparts. And this is the reason you get higher throughput for non-OFDMA in high traffic load, because ultimately you end up serving more number of frames. Okay. So, that was the case. So, therefore, this is the scenario, and then we understand that OFDMA has few overheads. What are the sources of those overheads? So, there is a preamble fail, then there is a multi-user block acknowledgement request and so on. So, these all come into play when you operating at a very high load, and in non-OFDMA in case of UDP there are no collisions also, then these overheads come into play. So, then we look at low traffic load, which is 5 Mbps. Which is the left hand side of this graph. So, this is the aggregate throughput 5 Mbps and this is the latency of the same scenario. Here you roughly see any difference between non-OFDMA and OFDMA, and so therefore, the suggestion would be that during low traffic load there is no reason for anybody to turn on the OFDMA feature, because non-OFDMA is equally well. No gain in throughput, almost equal latency. Okay. So, now comes the very interesting part, which is intermediate traffic load, which is 120 Mbps. So, in intermediate traffic load, what we see that throughput wise all are same. Non-OFDMA, all OFDMA configuration, everybody is able to achieve 120 Mbps. Throughput is everything good. The interesting part comes into latency. So, if you see latency, non-OFDMA has a higher latency than OFDMA 1. Here again our results corroborate with real experimental results, I guess, which is non-OFDMA is providing you lower latency compared to OFDMA counterpart. OFDMA providing you lower latency than the non-OFDMA counterpart. So again we tried to look deeper as to what was the reason that it was giving lower latency. Again we look at the aggregation statistics, and by looking at aggregation statistics, so this is for intermediate load. Okay. So the intermediate load, if you see the aggregation statistics, first of all the aggregation has lowered down from high traffic load for obvious reasons, and the aggregation is like kind of even lesser for lower RUs, which is also for obvious reasons because you have lower bandwidth for you to aggregate. So now if you see that for OFDMA, AMPDUs are mostly of size 1. Okay, and for non-OFDMA the AMPDUs are 3 and 4. So now if you tabulate this, it seems that again the same set of table that I prepared for high downlink traffic load, the total number of transmission non-OFDMA made within a TX of limit was about 22, and this was the case for others. Station served was this, the frames transmitted is exactly the same. Since the frames transmitted is exactly the same, that is where comes the throughput is exactly the same. But if you look at the station served, okay, station served is higher of course for 4 cross, 8 cross and 18 cross, and this is the reason you get lower latency in terms of intermediate traffic load, because in the aggregation graph also you saw that there was higher aggregation happening for non-OFDMA. That means there were packets who are waiting in the queue. There was more queuing happening in terms of non-OFDMA. There is less of queuing happening in OFDMA because multiple clients are getting served in parallel. So you could ask that this was happening in high traffic load also, but high traffic load did not see this happening, did not see that latency getting improved. That was because in high traffic load, so even though multiple stations were getting served all the time, but queue was always full all the time. So queuing delay, the packets has to anyway encounter. So then the takeaway from here is that we found out that for UDP the sweet spot for OFDMA is intermediate traffic load, neither low traffic load, neither high traffic load. Alright, so after getting a bit of understanding into UDP results, we moved on to TCP. The reason we started with UDP because UDP is very clean, you have only downlink transmission, no acknowledgement. Then comes TCP, in TCP you have TCP acknowledgements, and so TCP acknowledgements, if they are not supported over uplink OFDMA, then there is no point in doing the simulation. So NST does support uplink OFDMA support, and there is also a provision of BSRP, which is you look for, you send a buffer status request frame. So this is a downlink data coming from the stations. Then there is a multi-station block acknowledgement. Then there is a BSRP trigger frame that goes from the AP to the stations. Then the clients send their buffer status report through something called QoS null frames. Okay, and NST has a very specific configuration that these QoS null frames are sent in the form of 8 QoS null frames. Okay, so that has an implication that if time permits I will talk about that. So then there is again a basic trigger for that acknowledgements to go, and then the TCP acknowledgements go, and then for these also there is a multi-station block acknowledgement. This is TCP, this is MAC layer acknowledgement. Alright. Then we compared the results with UDP with TCP. So here again the x-axis is traffic load, y-axis is aggregate throughput. So if you see that for intermediate traffic load, throughput again is very much similar across non-OFDMA and OFDMA. But very interestingly, in high traffic load, there is one RU configuration which is 2 cross RU configuration, which turns out to be clear winner in terms of throughput. For some reason that we did not observe in UDP, we are observing in TCP that this OFDMA is providing you like one particular configuration of OFDMA is providing you higher throughput. Okay. So then we again looked at like what is the reason that this is happening. So then before that we looked at latency results also. Okay. So this is the latency results with respect to UDP, and these are the latency results with respect to TCP. So first of all you will observe that the latency has increased in TCP compared to UDP. That's for obvious reason that now the latency has to is increasing because there are TCP acknowledgements that the access point has to schedule, and because of which the downlink data frames are waiting in the MAC queue, and therefore the latency overall increases. So that's why you see that this is around I think 9 millisecond or something, and here it goes like 13-14 millisecond or something like that. Okay, it increases. There is and here like in terms of high traffic load, again there is no improvement in latency, which is similar to UDP, and in intermediate traffic load you again see that there is some improvement in latency when you are using OFDMA. So then like this is what OFDMA provides latency. Then we look at the aggregation statistics. So the aggregation statistics, so this is for high downlink traffic load, this is for the case of UDP, and this is for the case of TCP. So overall you see that for TCP you have the aggregation levels kind of has reduced. This is also for the reason that now within a TX hop you have to perform downlink data transmission and also uplink TCP acknowledgement transmission. So therefore your opportunity for the time for downlink data limits, and because of which your aggregation levels go down. Okay. So then this is for intermediate traffic load, and in intermediate traffic load compared to UDP you see a lot of like variations into aggregations that is happening, and that also we understood the reason for that, and there was very interesting dynamics was happening, which is TCP acknowledges every other packet. Okay, so if you have sent say 18 downlink frames, then that means 9 TCP acknowledgements will be created. If for some reason, for some RU configuration, if you break that data clocking, then the OFDMA won't be helpful. So that was one of the points. So this is again the simulation matrix like the table that we have created here. So if you see here that you will see that this is for high downlink traffic load, the total number of frames for non-OFDMA is kind of higher, that is why the throughput did not see any benefit for OFDMA. And for intermediate traffic load everybody was 82, and which is the reason everybody saw similar throughput. Okay. So we also find out, this is for TCP, that for high traffic load there was about 85% frames who faced collisions. Why did they face collision? Because for non-OFDMA you do not have the uplink support for sending the TCP acknowledgements, right. So now the data packets will collide with TCP acknowledgements of other stations, and that is why there was lot of collisions happening in the high traffic load, and in intermediate traffic load also there was collisions, but it was at a reduced rate. And here OFDMA played very well, because OFDMA had the uplink support to transmit the TCP acknowledgements, and that performed well in terms of improving the latency. Okay, so we also looked at queuing delay that was happening for UDP and TCP. Clearly TCP had higher queuing delay than UDP, for the reasons that UDP did not have to send those acknowledgements, the uplink acknowledgement that was getting generated by TCP, but TCP had to do, and because of which the queuing delay at the MAC layer of the packets for TCP had increased. Okay, so to conclude that we found out that actual benefits of OFDMA can only be extracted under intermediate traffic loads for both UDP and TCP, and under high traffic load only for a few specific RU configuration TCP provided higher throughput. So that was the takeaway from the simulation results, and then we again contributed towards looking at various application scenarios, how OFDMA provides comparison to non-OFDMA in various application settings.
Hello, ma'am. I have actually two questions. First is, does NS3 support TGX proposed channel model in order to capture the frequency selectivity nature of the fading channel? Second is, like, what are the channel impairments considered in the simulation other than signal attenuation?
Okay. So this was, as I said, this was at the best condition that could have been achieved. We did not apply any like fading model, any channel impairments. So it was the best condition. Everybody was MCS 11. There was no channel like no fading model, no path loss model, anything like that. To make sure that even in the best scenario, what happens? Do I see OFDMA giving improvements? But NS3 does support channel modeling, so you can have frequency selective fading, like relay fading sort of thing. You can have flat fading scenarios.
Can you please explain how are you measuring latency?
Sure. So the yes.
And let me finish. Like, are you measuring latency in TCP traffic as well as UDP using IPerf or some other tools?
Using
IPerf or Chariot or some other tools? How are you measuring the latency in your simulation setup?
You're done? Yeah. Okay. So the simulation results, so since this is simulation, so it was very easy to compute the latency. So we know that when the packet left that AP and when it reached at the station. So here we could not do IPerf because this was in simulation. So what we did is that it was a long download that was going on, and for UDP also long download going on, for TCP also long download was going on, and the stations were sending acknowledgements. And we computed both MAC layer latency, like MAC layer queuing delay and transport layer queuing delay. Both of them we computed.
Yeah, I think question from you.
Yeah, I have two questions. So, what was the payload for all these three scenarios?
1000 bytes.
But you didn't try for the lower bytes?
Yes, we did try for lower bytes.
And what was the result?
Yes, so for lower bytes there was very interesting results. What we obtained that for lower, so we actually went from 1000 byte to 30 byte. So all the things we tried, 250 byte, 100 byte, 90 byte, 30 byte. So as you go on reducing your payload size, the improvement of OFDMA increases, and OFDM like kind of provides suboptimal performance.
Yeah, it will be good, nice to see those results, because hopefully I think with lesser payload we will see the gain.
Sure.
That is the first question. Second, can you show me, you told right under few RU config for the TCP you are seeing the OFDM again. Which is that scenario?
That was 2x242.
But how it is done? Means how the OFDM is showing the, what is the reason behind that?
So the reason is the number of transmissions. So we found out that 2x242 did more number of transmission compared to non-OFDMA. So
can you little explain, or we can?
Yes.
I think in interest of time.
Sure.
So okay. So privilege as a speaker.
Yes. One question needs to be asked, not to you, to Srikanth. So two successive presentations, they have showed using different methodologies that unless you have a full buffer traffic, the latency is better with OFDMA than with non-OFDMA. Full buffer traffic, OFDMA is overhead is more than the return. So would you still compete that OFDMA is not a useful feature? I thought this is important because this has been the theme of discussion.
So you put me in a spot. I don't want to delay him. So maybe I will, let's grab some time from the other presentation. So I think I'll still stand by that statement that I'm still not seeing consistent performance, but I'll take your comment and results from Alithya and Mukulika. So we'll debate about that. So thanks Mukulika. I think we'll get Mohita.